Hello everyone. Welcome to JCE Connect online classes. Today let us look into Module 4 Embedded System Design Concepts, one of the fundamental topic that is program modeling. In case of hardware-software co-design system, selecting a model is considered as one of the fundamental issue. The use of this model helps the embedded design for capturing and describing the system characteristics. So every embedded system design include 6 of the following computational programming models. The first one is very simple one, data flow graph model. It is in short called as DFG model. Second one is control data flow graph model, which is the further continuation of data flow graph model considering control instructions. Third one is state machine model. In this we are going to study finite state machine model also. Fourth one is sequential program model, which includes a flowchart. Fifth one is concurrent or communicating process model. And the last one is object oriented model. So let us discuss these programming models one by one. Now let's understand the data flow graph model, that is in short called as DFG model. The diagram of the same is given here. So let us understand what is a data flow graph first. It is the model which translates the data processing requirements into a data flow graph. It is a model which is a data driven, in which the program execution is determined by the data given as an input. It consists of the data and the operations on the data which transforms the input data into output data. Indeed, this flow graph is a visual model in which the operation on the data is processed and represented using the block that is known as circle, and the data flow is represented using arrows. An inward arrow to the circle represents input data, and an outward arrow from the circle represents output data. In this DFG model, a data path is the data flow path from input to the output. This model is said to be acyclic if it doesn't contain multiple values for the input variables and multiple output values for a given set of inputs. That is, if it doesn't contain feedback as well as event. Here feedback inputs, that is output fed back to the input, and events are some of the examples for cyclic inputs. And this model translates the program as a single sequential process execution. Embedded applications which are computationally intensive and data driven, which are modeled using this flow model. Digital signal processing applications are typical examples of it. Now let us look into one basic implementation by taking example, and the diagram of the same is given here. So it includes two nodes, those are known as data flow nodes, which indicates the operations. And for the first data flow node, A and B are the two data inputs. The first node acts as a addition operation which adds input data A and B and produces the output as X. For the second data flow node, which performs subtraction operation, which receives X and C as the input and produces Y as the output. This is how the data flows from one step to the another step. Here the basic inputs are A, B, C, which are given data, and Y is expected output. So this way the data flow graph travels from input to the desired output. The second model is control data flow graph. It is in short called as CDFG. We have seen in DFG, that is data flow graph model, which is data driven model in which the execution is controlled by data. It doesn't involve any control operations or conditional operations, but thus control data flow graph is used for modeling applications involving conditional program execution. This model contains both data operations and control operations. This uses data flow graph as element and conditionals as decision makers, and it contains both data flow nodes and decision nodes, wherein data flow graph contains only data flow nodes. So let us look into one of the implementation example. Let us consider if flag is equal to 1, then perform x equal to a plus b, else perform y is equal to a minus b. Here the condition used is if flag is equal to 1. So this requirement contains a decision making process. So the control node is represented by a diamond block in the given diagram here, which is a decision making element in a normal flow chart based on design. So which translates the requirement which is modeled to a concurrent process model. The decision on which the process is to be executed is determined by the control node. So let us take some of the examples which uses this CDFG in real world. So first example is like capturing and saving the image to a particular format that is set by the user in digital still camera, where everything is data driven, starting from analog front end which converts the sensor generated analog signal into digital signal, and the task which stores the data from ADC to a frame buffer for the use of media processor, which performs various operations like autocorrection, white balance adjusting, etc. The decision on which the format the image is stored, the formats like JPEG, TIFF, BMP, etc. is also controlled by camera setting configured by the user itself. So these are the real world examples of this CDFG model. And the third model is state machine model, which is used for modeling reactive or event driven embedded systems whose processing behavior are dependent on state transitions. Embedded systems used in the control and the industrial applications are typical examples for event-driven systems. The state machine model describes the system behavior with states, events, actions, and transitions. Here, the state is a representation of a current situation, and event is an input to the state. And the event acts as stimuli for state transition, and the transition is the movement from one state to another, and the action is an activity to be performed by the state machine. A finite state machine model is one in which the number of states are finite. In other words, the system is described using a finite number of possible states. As an example, let us consider the design of an embedded system for passenger seat belt warning in an automotive using finite state machine model. The system requirements are captured as first case, when the vehicle ignition is turned on and the seat belt is not fastened within 10 seconds of ignition on, the system generates an alarm signal for 5 seconds. The second is the alarm is turned off when the alarm time expires, or if the passenger fastens the belt, or if the ignition switch is turned off, whichever happens first. Here the states are alarm off, waiting, and alarm on, and the events are ignition key on, ignition key off, timer expire, alarm time expire, and seat belt on. So the diagram given here shows the FSM model for automatic seat belt warning system. Let's understand the diagram which is shown here. The ignition key on event triggers the 10-second timer and transitions the state to waiting. If a seat belt on or ignition key off event occurs during the wait state, the state transitions into alarm off. When the wait timer expires in the waiting state, the event timer expire is generated and it transitions the state to alarm on from the waiting state. The alarm on state continues until a seat belt on or ignition key off event or alarm time expire event, whichever occurs first. The occurrence of any of these events transitions the state to alarm off. The wait state is implemented using a timer. The timer also has certain set of states and events for state transitions, which we'll discuss later. Now let's understand the timer set of states and events for state transitions. As seen from finite state machine, the timer state can be either idle, ready or running. During the normal condition, when the timer is not running, it is set to be in the idle state. The timer is set to be in the ready state when the timer is loaded with a count corresponding to the required time. The timer remains in the ready state until a start timer event occurs. The timer changes its state to running from the ready state on receiving a start timer event and remains in the running state itself until the timer count expires or a stop timer event occurs. The timer state changes to idle from running state on receiving a stop timer or timer expire event. Here I have taken one example to design an automatic tea or coffee vending machine based on finite state machine model by considering the requirements like the vending machine is initiated by the user by inserting 5 rupees coin. After inserting the coin by the user can select either tea or coffee or can press cancel button to cancel the order and take back the coin. So the representation of finite state machine model is given here. It consists of 4 states. State A, wait for coin. State B, wait for user input. State C, dispense tea. State D, dispense coffee. Here the event insert coin, that is 5 rupee coin insertion, transitions the state to wait for user input, and the system remains in the same state until the user input is received from the buttons like cancel, tea or coffee. Tea and coffee are the drink select buttons here. If the event triggered in wait state is like cancel button press, then the coin is pushed out and the state transition back to wait for coin state. If the event received is like tea button press or coffee button press, then the state changes its state to dispense tea for tea button press and dispense coffee for coffee button press respectively. Once tea and coffee vending is over, the respective states transitions back to wait for coin state, that is state A. This is how the finite state model works with the design of automatic tea or coffee vending machine by considering 4 states. The remaining 3 programming models will be discussed in the forthcoming videos. Thank you everyone for watching.